And now to get started, I would like our moderators today to introduce themselves. And first, I'm going to invite on Dave Heidel. He's our UVDI Director of Global Airside Sales. I'm going to welcome Dave in. Dave.
Thanks, Andrew. As Andrew mentioned, I'm our Global Sales Director of the Airside Sales Team, and the sales team is on the webinar with us today, and on behalf of myself and them, I'd like to welcome everybody today's webinar. As Andrew said, today's webinar is all about furthering your comfort with UVC air disinfection, and to do so, my colleague, Dr. Ashish Mathur, is going to address some of the common questions that you've shared about UVC, UVC air disinfection, and ASHRAE 241. Then, true to today's town hall format, we're going to be turning to you to capture and address your questions. Now, to ensure the question function is working properly, I'd like to do a quick test. So in the question box, please type in the state, province, or country that you're joining us from. And then also, if you have joined us in our very first webinar on coil cleaning, please type in yes. So type in where you're joining us from and whether you attended our first presentation. All right, I see them coming in. Tyler from New York, John from Florida, Edward from Maryland, Christine from Texas, that's our VP of Sales. We have Richard from BC. We have Toronto, London, South Carolina, Portland, Florida. So as Andrew mentioned, I want to welcome everybody from all over the globe. Now, without any further ado, well, actually, let me mention one more thing. We're going to be doing some polling during the webinar, and this is going to give you a chance to provide your feedback, and we'll go over those as we come to them. But now, without any further ado, I'd like to turn it over to Dr. Ashish Mathur. He's our Vice President of Innovation and Technology, to introduce himself and kick off today's webinar.
Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. And thank you for joining. If you might have run into me at ASHRAE, this is a perfect tee up to the ASHRAE conference, which is coming up in a few days in Indianapolis. I'm currently chair of the UV Technical Committee at ASHRAE, and I'll be running a couple of meetings on Monday, next Monday, related to our UV. I'm also active in the International Ultraviolet Association, IUVA, where I'm leading the industry working group, which is focusing on everything related to UV in public spaces. So I wanted to get started on the webinar here. So, of course, SARS-CoV-2 opened all our eyes, and we're probably here because of that, learning about ultraviolet because of that. But certainly the issues of indoor air quality far extend beyond that. Other serious airborne infections such as the flu, tuberculosis, and we've heard a lot about measles recently, they continue to cause widespread illness and deaths annually all over the world. In addition, the quality of the building ventilation directly affects the relationship between airborne transmission of respiratory infections and the health and productivity of workers. So for this topic, we have a few learning objectives. I'll go over the fundamental aspects of airborne transmission, review in brief the various mitigation approaches that are currently available to us to reduce the transmission, and then take a deep dive into UV technology, how it works, how and where it can be deployed, what are the associated standards and guidelines by the industry and government agencies recommending its use. And then in the town hall format, we'll review common UVC air disinfections questions which we are generally asked related to effectiveness, correct application, and so on and so forth. And then towards the end, we'll talk about the new ASHRAE 241 standard, which came out last year, which is the control of infectious aerosols, and then see how UVC technology can fit in and help meet that standard. And then we'll open it up to answer your questions about UVC air disinfection. So before we get going, I would like to do a quick poll, and I'll hand it over to Dave to run that first poll. related to this.
Thanks, Ashish. As you can see, our first poll is going to be, what do you see as the greatest benefits of UV technology? And please select your top two. I'm going to launch the poll here, and you'll be able to respond. I'll give you about 15 seconds or so. So please select the top two, and then we'll review the results. Great, I see everybody's responding, and we've got a variety of responses. So we'll go a couple more seconds, and I'm going to close the poll now and share the results. So as we can see, top one, improve indoor air quality as one of the top benefits that you see for the use of UV technology, with reduced sickness and absenteeism right after that, but a good mix of all of the items that are here. And these are topics that Ashish is going to be covering throughout the presentation. So I'm going to close out the poll and turn it back over to Ashish.
Thanks, Dave. And actually, this was a really good response and good understanding, because when you go back a few years, even before COVID, UV technology was always like a value add or a value proposition, and it was more about, okay, am I saving energy? Only then I'm going to apply UV. But now the focus has shifted, and people are more concerned about indoor air quality. It has really come center stage, and of course, affecting the sickness and absenteeism at the workplace. And I think the reason is, when you go back 40, 50 years ago, indoor air quality was not so much of an issue because we were naturally bringing in fresh outside air and diluting the concentration of the biological contaminants and chemicals that were trapped inside the building envelope. But now that we are spending more time inside, and the buildings are being built so tight, and we're not bringing in enough fresh outside air to dilute these contaminants, it's becoming a concern. Studies have actually shown that the air inside our homes are 2 to 5 times more polluted in terms of biological and VOCs and odors compared to outside. So to understand the transport mechanism of these microorganisms, we need to understand the size. So this air contaminant chart shows relative sizes of the different types of pollutants which are found indoors and outdoors. If you see the scale of this chart at the bottom, it's in micrometers, which is 1,000th of a millimeter. So when you compare it to the size of a human hair, which is around, say, 60 to 100 microns, spores are a fairly large number, are big in size, 10 to 30 microns. Then you have the bacteria, which ranges from 1 to 10 microns, and the viruses get into the less than 0.1 micron. And we know the SARS-CoV-2 was right around 0.012. Gases contaminants and VOCs, which are responsible for odors and related health issues, are on the extreme left, are in the nanometers and angstrom scale. So it gives you a snapshot of, okay, you have a wide range of contaminants with different sizes. So you have to look at control strategies which will be effective against all of these. So there's several studies which talk about what are the microbial contaminants in buildings, and this is a list which has been generated from all the studies. And you can see pretty big names there. I'm not going to read all of them, but there's a whole category of bacteria. Some of that stuff is coming from outside. Some of it is growing inside the ductwork. Some of it is growing in the coil. Viruses are, of course, coming from outside and being circulated inside the building as the occupants may be infected and the air is circulating. And of course, hopefully, the mold and fungus is only coming from outside and not from inside. But Aspergillus niger is really at the top of the list, where we've heard of some hospitals which have closed down because of Aspergillus niger outbreaks. Then, of course, we have SARS. So initially, of course, people were saying that SARS is only surface, And then there was some concern about, is it really airborne? But since then, there have been several studies which have showed that SARS-CoV-2 is actually can be transported and transmitted through the HVAC system. The presence of SARS-CoV-2 has been reported at several locations along the HVAC system in the air return and supply pathways, including multiple locations in the air handling units. So when you look at the different vectors of microorganism transmission inside buildings, again, like I said, there are different particles and the mode of transmission is different. Airborne transmission is mainly due to aerosols, where the small particles are carried and transported by the air currents to large distances and linger in the air for long periods of time. Droplets, which was initially the case, droplet transmission is typically short distance, where droplets are transmitted as projectiles to people, surfaces, and objects only in the immediate vicinity. And I think the rule of thumb was 6 feet, and that's why we had that 6 feet distance rule proposed by the CDC. So droplets don't really linger in the air, and the size dictates how long they can remain suspended in the air. But these droplets can really dry out, and as they dry out, then you have the aerosol which gets transmitted. When you look at the size chart at the bottom, the virus size chart here, you can see the really small sizes of the viruses. Some of these viruses, as an infectious person is emitting, most of these are kind of enveloped in a respiratory fluid initially, and then as it dries up, the size goes down and then it can be transported. So of course the size dictates how long it stays afloat, how far it can travel, and how efficiently control strategy could be applied to that. So this is a slide which of course a lot of people would be familiar with. What are the different engineering control strategies which we have? And like I said, the air contaminant chart showed their particles of different sizes, transmission modes are different. So there is no silver bullet that can address all these transmission modes and therefore require multiple strategies. And of course, our first line of defense is of course ventilation whenever we can. Ventilation involves purging the space or increasing the air changes per hour, which we are all familiar with that terminology. That is diluting the space with bringing in fresh outside air, fresh, clean outside air, I would say. Or especially in healthcare settings, you can have control by pressurization. You can have positive pressure rooms, negative pressure rooms, and isolation rooms. And then once you've gone through the ventilation and dilution as a primary defense, then you start looking at what are my air cleaning and disinfection strategies, filtration being the first one, and then of course UVDI and some other emerging technologies could be used as well. So when you look at the whole building envelope, you can have things which, of course, after ventilation and dilution, you can have technologies which are installed in the main ductwork, in the central air handling system, or you can bring technologies and implement them at the room level as well, if you want any localized control of infection. So Pacific Northwestern National Lab, which is affiliated with the Department of Energy, has been evaluating GUV over the past couple of years heavily, and you can see some of their communication on the internet, and you can get to the site. And they've recognized that GUV offers benefits as more effective and an energy efficient alternative over increasing ventilation loads above code limits. So 62.1 gives you a basic ventilation limit. This is what you need to have, and that's kind of prescriptive. But if you need to go above that for any control of infectious aerosols or to get a higher air quality, you need to look at other technologies. So what GUV offers is an alternate to increasing your ventilation load. So you provide the code level, maybe you don't have to go above it. So use GUV as a more effective and energy efficient alternative to, for example, demand control ventilation. There is also a decarbonization opportunity, especially in northern climates. If we can avoid increasing the amount of outdoor air that we're bringing in above code, that's directly related to fossil fuel heating. And for those out there that may be involved in building electrification efforts, we see a potential benefit of this technology as well, whereby reducing the outdoor air ventilation load, you're going to reduce the required size, cost, and infrastructure requirements of, say, a commercial heat pump, potentially making that electrification measure to replace a fossil fuel heating system with an electric heat pump to be more cost-effective solution. So there are numerous published studies demonstrating the effectiveness of UV technology in improving air quality by disinfecting the airstream, whether it's in the duct or at a room level. So here you can see the applications. Of course, cooling coil disinfection has been the first and the foremost application for applying UV inside buildings because the cooling coil harbors a growth of both bacteria and even mold growing on the cooling coil. Air disinfection solutions for UV can be applied inside the central air handling system or inside the duct. So you don't have to, if you don't have the space or you only focused on a certain part of the building, then you would just install the UV system in the duct. And then at a local area or a room level, there's upper air UV and ceiling mounted UV, which has been used. And of course, the advent of room air purifiers, which include UV as a technology is also used. And then inside buildings, especially in healthcare, you have portable whole room disinfection devices, which go in and treat the whole surfaces of the room. Or you can mount a UV in your ceilings or mount them on the walls to get the UV disinfection. So here are some pictures. This is a cooling coil, and you have a UV system in front of the coil, which is designed to could be designed to just treat the coil, or could be designed to treat the air, or both. And this is a picture of how lamps could be installed inside the duct, where the lamps are ideally placed parallel to the duct. Here's a picture of an upper UV application where you can see that the UV fixtures are installed only above 7 feet in a room, and they're only shining in the upper part of the room because UV is harmful to eyes and skin. So there are louvers on these fixtures which are only focusing on the upper air of the room and disinfecting the air on the top. Or you could have ceiling mounted UV lights. Depending on the wavelength you have, you would have to have effective safety interlock switches to turn them off as needed, depending on the occupancy in the room. Right, so this is the time to do another poll. And Dave, I'm going to hand it over to you to run this poll.
All right, well, thanks, Ashish. Okay, you can see the poll here. The question is going to be, do you currently use or specify UVC for air disinfection? And we have representatives from users, owners, facility management, as well as engineering firms and distributors. So it could be a different type as far as whether you're specifying or selecting. And we want to just get a sense of that. So I'm going to share the poll, and we'll have about 10 or 15 seconds. And please select one for this poll. All right, great. I see the responses coming in. We'll go a couple more seconds. And I'm going to close now, and we will share the results. Okay, so it looks like number one, yes, my company specifies UVC for air disinfection. Great to see. Yes, and we can see about 13% do have them already installed in the facility, and a large percentage that are not currently using but are interested in. And we're hoping the information we provide for you today is going to help you answer any questions you might have related to that. And also, for those of you who are not sure, that's really the main purpose today for us, is to give you as much information as we can to help you understand the value. I'm going to close the poll now, hide it, and we will turn this back over to Ashish.
Right. So yeah, so that's a good mixed response from the audience, and hopefully the next few slides will help people who are new to UV and people who are not sure about how do we specify UV, and give some high-level information. And of course, later on we can get into more details on a one-to-one basis. So just a quick overview of UV, how it works. UV belongs to the let's call it the ultraviolet spectrum. UVC is specifically in the range of 200 to 200 nanometers, and is considered and proven to be germicidal in nature, means it can kill microorganisms. The most important aspect of UVC is that most single cell microorganisms show a high absorption of UV. This is a DNA curve which you see here, and you can see a very high absorption in this range of 250 to 275, 280 nanometer range. So because these microorganisms absorb UV in this range, they can be killed by it or inactivated by it. And just as a gift of nature, the low pressure mercury lamps, which are used worldwide and ubiquitously, is ideally suited for this application because greater than 90% of their output is right at 253.7 or 254 nanometers, so very close to the peak of this DNA absorption curve. So the UVC light, low pressure mercury lamps are like ideally suited suited for each other, if you may. The mechanism is pretty well documented and proven that if you look at the DNA or RNA of structures, when UV light shines on it, it basically kills one of these bonds inside, and it kind of prevents the DNA from replicating. So if it stops replicating, it basically the cell dies automatically and cannot inactivate anymore. So there's so many studies out there, and since it's a proven technology, I don't really have to get into too much detail on this, but there are several studies which have correlated the benefits of UV technology to workers' health and well-being. There have been studies done by EPA, a couple of studies in the last year by the EPA Indoor Air Quality Group on UV. The World Health Organization, CDC, they all have documents and guidelines to prevent the transmission of tuberculosis. And then, of course, when SARS-CoV-2 happened, there was a flurry of research activity confirming that UVC is effective against SARS-CoV-2 and similar viruses. So while the DNA structure is damaged by UVC light, the susceptibility is affected by the unique shape, sizes, cell structure. All these microorganisms are different. So it's not just the size, but it's also the photochemistry, the cell chemistry on absorption. So even though they're all affected by UVC, there are relatively, some are easier to kill and some are more difficult to kill. For example, viruses are, I would say, easiest to kill, followed by bacteria and then mold. So if you look at these, what is the UV dose required for a 99% kill or inactivation? And you look at these numbers, you can see SARS-CoV-2 actually is one of the easiest to inactivate when you look, compared to other microorganisms. And the studies which were done in the past few years have confirmed that you just need, say, a dose of 1222 microwatts per centimeter square to get 99% kill for SARS-CoV-2. And we've been always modeling our airstream disinfection system using influenza because that's every year, and we have the seasonal flu, and that really requires a much higher dose compared to this SARS-CoV-2. And then bacteria and molds are, of course, the mold, of course, is way orders of magnitude over this. So they are susceptible at different degrees. So when you look at how do you size a UV system, you have to really look at, okay, am I sizing it for viruses or am I sizing for bacteria, or do I really want to size it for mold? So it's important to to understand that. So which brings us to what is the most important parameter which you design a system to, and that is the dose. The UV dose is the single most requirement. The dose applied is the cumulative intensity reaching the target area multiplied by the exposure time. So to increase the dose, you can either increase the intensity by either increasing the number of lamps, UV lamps, or if you can increase the exposure time or dwell time. Keep in mind that, of course, in an airstream application, air is moving pretty fast at, say, almost 400, 500 feet per minute. So your exposure times are less. So, and we'll get into that a little bit later. So here's a quick summary of the main differences between, say, a coil and an airstream disinfection. A coil disinfection, you have a coil and the lamps are just in front of a coil, and you have pretty much an infinite amount of time to disinfect it. So you don't need a whole amount of UV. In fact, the ASHRAE guideline says that if you can have an average intensity of 50 to 100 microwatts on the coil surface, that's fine, because these lamps are on 24/7, and the light will focus on the coil and it will penetrate through the fins of the coil and take advantages of the metallic reflectivity inside the coil to get to that higher dose level over time. On the other hand, airstreams, like I said, 400, 500 feet per minute in the air handling system, or even up to 1,000 feet a minute, or even higher in the duct, you don't have that much exposure time. So when you look at sizing a system, it's not the same. Of course, you have to look at the lamps. Some lamps have lower output than the others, and that will have an impact on the energy. So for a coil application, you can decide which kind of lamp is more effective. Maybe you need 10 lamps, which are standard output, but you can just do the same thing with 2 lamps, which are high output. So you can design it different ways. So modeling a system is really useful in figuring out what is the best way to design the system for that application. So ASHRAE has, they formed an epidemic task force during COVID, and as a result of that, they came out with some standard guidelines for how much UV dose you need for intact air disinfection, and then what is the dose you need for SARS-CoV-2. I showed you the number in that susceptibility chart for SARS-CoV-2, it was 1200, but basically what they're saying is if you have a minimum of 1500 microwatts of UV dose applied in a 2 feet region, that would be sufficient for sizing the UV system for airstream disinfection. And over the last couple of years, CDC has come out, and I wouldn't say endorse it. They've updated their ventilation guidelines, and they talk about using UV as an effective mitigation strategy. So they talk about intact UV as well as upper air UV as an effective mitigation technology. So time to another poll, to do another poll, Dave.
All right, thanks, Ashish. Okay, on this poll, question is, when you're looking at using a UV system, how do you specify that? And you'll see the questions or the answers. You follow industry guidelines. You have a system provider, a representative that you work with. You either hire a consultant engineering firm. You might have another way, or you may not actually be specifying it yet. So if I get a sense here, I'm going to launch this, and we will go about 10 seconds. So please provide your response to this one. All right, I see the responses coming in. Thank you. Also want to let you know that through the presentation, if questions come to your mind, you can go ahead and type them in the question box, and they'll be ready for us at the end when we actually start to get into the Q&A. So don't hesitate to type. We will respond at the end of the formal presentation. Okay, I'm going to close and share the results. So it looks like over half use a UV system provider, work with a representative or perhaps manufacturing firm, and then followed by looking at industry guidelines, And then we do get a good sense of people who are not currently specifying them. Again, the information we're providing today, we're hopeful that you'll be able to use that. I'm going to close out the poll and turn it back over to Ashish.
Thanks, Dave. So I think what we're finding is the pandemic unfortunately spawned a lot of new startups and companies who have provided unvalidated systems and misapplied the UV. So we've seen specs which are really designed for coil disinfection, but the claims have been made that they will also do airstream disinfection, so which is not really true. So for illustration purposes, this example below, like I said, ASHRAE says for a coil application, you just need, say, 100 microwatts. So if you have 100 microwatts, and you look at an airstream application where the air is moving at 500 feet per minute, that applied dose is only 24 microwatts, whereas the target is 1500. So there is no way you can get the dose you need to get a decent amount of UVC disinfection for airstream. Even if you go 10 times, 100 to 1250, your dose is only 300. So it still falls short of what you need for air disinfection. So yeah, so coil disinfection by itself cannot, but yes, you can use that same system. And if you have the system in place and it's a retrofit application, you can actually beef up your coil application system by adding more lamps, making sure you work with the manufacturer to figure out what is that number of rows of lamps and number of lamps you need to be able to get to a reasonable level of airstream disinfection. So here's an example that, okay, going from a 3-row coil system to a 5-row coil system using our lamps, we were able to get to at least 90% disinfection of SARS-CoV-2. And we have third-party validated data to prove that. So there are differences between air handling system and in duct. Like I said, of course, air handling systems, the airflow speeds are less. In a duct, the airflow speeds could be higher, and that way your exposure time is going to be less. So when your exposure time is less, you need a higher intensity. So the y-axis on this graph is intensity, the x-axis is exposure time. So if your exposure time is less, which is the case in duct, you would need a much higher intensity, whereas inside the air handling system, say around 500 feet per minute, you need lower dose. And this table on the right shows that how much extra dose you would need to go for, say, from a 99% disinfection of coronavirus to 99.9, and then and then for influenza. So what I wanted to bring out here was, say, a 99.9% disinfection of coronavirus could be equivalent to a 90% disinfection of influenza. So what are the key parameters that impact UV intensity? We talked about microorganisms. There are some new technologies out there with different wavelengths, so you want to make sure that the system is sized for the output of that lamp, whether it's an LED or 5UV or some other UV source. The what if, the configuration of lamps in the space, wind chill is important. This graph shows that the velocity in the duct and the air temperature in the duct has an influence on the lamp power. So when manufacturers like us are designing systems, we factor in what is the temperature of the application by installing it close to the coil where the temperatures are different compared to something way downstream of the duct. The humidity levels, the reflectivity available in the duct also has an influence. So all these parameters are important. And the most important thing is, like any light technology, UV follows an inverse square law. You go further away from a light source, the intensity drops. So if you go twice the distance from a light source, the intensity drops by 1/4, and so on and so forth. So modeling is important. You can't just say, okay, I got so many lamps and this is my total output which I'm sizing. It also depends on how you're placing the lamp. So the modeling really helps figuring out what is your intensity or dose profile inside the duct. So here's an example which shows that here the lamps are spaced evenly along the duct. So these are in the corners and you get a fairly uniform profile versus if you bunch all the lamps in the center, your distribution inside the duct is much narrower and not uniform. All right, Dave, time to do another poll as we get into a discussion about ASHRAE 241.
All right, thanks, Ashish. So the question here, how familiar are you with the ASHRAE 241 standard? How familiar are you with the standard? The rest of the presentation is going to be focused on that, and I'm going to share, I got to technical launch, there we go. So please select one. We'll have it open for about 10 seconds. I see the responses coming in. It's great. Okay, we are going to close out and I will share the results. So it looks like over half were aware of the standard, but don't really know the details. And I think that's a typical category right now with it. And we do have good percentage not familiar with the standard. So, you know, the purpose of the rest of Ashish's presentation is high level. There's a lot of details in it, and we're going to brush on the top of it. But it looks like most everybody knows of the standard. So that's good to see. I'm going to hide the results now and turn it back over to Ashish.
Right. Thanks, Dave. So yeah, this ASHRAE 241 standard was a really high priority effort from ASHRAE, driven by a request from the White House, and they formed a committee of really highly respected committee members, and they came out with the standard for the control of infectious aerosols in buildings. Until this, there was no standard on what do building owners do to combat any infectious aerosol in a building and transmission. There was nothing out there. So this standard was fairly quickly put together in a very concise way. So what it does is it establishes minimum requirements. So what ASHRAE does is, like some of the other standards do, they always establish minimum requirements. So what are the minimum requirements for control of infectious aerosols to reduce the risk of disease transmission in occupiable space of new and existing buildings? So it's pretty important purpose. So it's different from 62.1. It does not establish overall requirements for acceptable air quality. It's only focused on reducing the risk of disease transmission. So there, if you really want to get into the details of 241, I would say there's like so many presentations which you can access on the internet, YouTube, and Dr. Ben Banfleth and his team who spearheaded 241. They've been really putting the word out. And there's also an ASHRAE learning webinar available on demand, I guess, which you can go and get learning credits for 241. So some of the basics, important things are, it builds, it does not replace, it builds on the standard 62.1 for commercial buildings, 62.2 for residential, and 170.1 for healthcare buildings. So that's your baseline. So it says you got to meet all these requirements, and then on top of it, you need to put ASHRAE 241. And the main thing which is highlighted in blue is that infectious risk management mode. It provides additional ventilation requirements for periods of elevated risk. And the metric which they're using is called the equivalent clean air flow rate, which is the theoretical flow rate of pathogen-free air that would have the same effect as bringing in fresh outside air. So it brings you the concept of you don't have to just rely on outside air. You can replace that outside air with maybe more energy efficient ways than just bringing in outside air. And then it gets into a little bit more details. Buildings need to have a building readiness plan, and then it goes into the different discussions on what are the filtration air cleaning technologies and how do you measure that, how do you calculate those things. So the important thing is, in a risk management mode, your occupancy could be different. So for example, when we were all working remote, you don't have to run that building full-fledged, right? The occupancy is less when people are working remote. So when you design your system to meet 241, you have to look at what is the occupancy. So what they've done is that they've said, okay, the equivalent clean airflow calculation is going to be based on your design occupancy, number of people present in the breathing zone. So here's an example or a comparison of the current 62.1 and ASHRAE 241. According to, for these three examples, restaurant, dining room, classroom, and office. For 62.1, the CFM per person is 10 for a restaurant, and it goes up to 60 for 241. For a school classroom, it goes from 13 to 40, and for an office, from 17 to 30. So you can see that it's like the increase is pretty significant. Like for a restaurant application, it's the six-folds. And the columns on the right show you the equivalent air changes per hour related to that. So 62.1 does not address airborne transmission. 241 does. So you need to take that into account. So what 241 says is you can replace the outside air by a combination of different technologies. If you have all these things at your disposal, you can have things in the duct air cleaning systems, fibers, and in-room air cleaning systems, filters, or you can do pathogen inactivation by induct UV, and things which we just talked about, or in-room UV using upper air, ceiling mounted, or portable air cleaners employing UV technology and other technologies. So it allows you to reach that equivalent clean air goal by combining these systems. And in addition to performance, they say, okay, how do you test your system to make sure that you meet the equivalent clean airflow rate? So so they've chosen a microorganism, which is MS2 virus, which has to be tested according to whatever available standards they are. So for UV technology, for airstream in a duct, it's 185.1. If you and for a room, they have something in the normative Appendix A. And then in addition to performance, you have to look at safety as well. So whatever system you apply, make sure you're not exceeding the limits for PM, ozone, and formaldehyde levels as defined in the standard. They also show a calculator where you can look at the contributions of different technologies. So you can use a calculator where you know what is the outside air, and then you can look at the contributions of the different technologies, and then you can sum them up, and it will tell you whether you pass or fail. So just a more expansion here. So in the calculator, it says, okay, UV in your HVAC system, in your duct, what is your single pass inactivation? And that will give you some points, and it will calculate that equivalent clean air CFM based on those numbers. If we have UV in the room, whether it's in the form of an air cleaner or upper air system, you can add those things here, and it will count towards your final equivalent clean air. So again, PNNL lab, like I mentioned earlier, they are currently doing studies, and they basically said, okay, you have all these things at your disposal: outdoor air filtration, induct UV, upper air UV, portable air cleaners, ceiling mounted UV. These are your tools in your toolbox which you can apply for this. So yeah. So before we end, I want to do one more poll, and I'm going to hand it over to Dave. Dave?
Thanks, Ashish. And as you can see our poll question here, what do you see as challenges in deploying UV technology with your clients or in your projects or in your building? And I'm going to share the poll. I have about 10 seconds for responses. And please select one. All right, great. I see the responses coming in. Go a few more seconds. Okay, I'm going to close now and I will share the results. Oh, looks about the same between limited understanding of UVC technology as well as resources to install, operate, and maintain as two of the challenges. Hopefully, again, some of the information we provided today will help with the understanding of it. And certainly, we'll have contact information available at the end for you to be able to reach out and answer any of the other questions that you might have regarding the challenges that you do face. All right, I'm going to close here and turn it back over to Ashish.
Right, thanks. So we're going to close up by saying that, okay, in summary, domicile UV technology is a proven technology. It's been validated and it's recommended by ASHRAE and CDC and other organizations. It can be effectively applied not just for coils but also for airstream disinfection in an HVAC system and for in-room disinfection. And then, of course, to have a successful implementation strategy, you've got to make sure that you're sizing your system correctly, and then make sure that you're installing it as per the manufacturer's guidelines and following the applicable regulatory and safety standards. So with that, Dave, I'm going to turn it back to you to read out the questions which may be coming from the audience.
All right, great. Thanks, Ashish. Yes, we do have some questions coming in, so I'm going to get through as many as I can. If you have any additional questions, please type those in. First one is a question from Tyler. Where can the ASHRAE 241 equivalent airflow calculator be found?
So if you go, you can access the ASHRAE 241 or you can purchase it. And if you go to one of the appendixes, towards the end of the appendix, there is a link to the calculator. Actually, if you go on the ASHRAE website and you put in 241, you'll see it. But I have your email address. I can send you the link to that calculator, Tyler.
Okay, thanks, Ashish. Next question: are the doses that we were talking about in slide 16, or what are they displayed in? The question had MJ/CM2, but I think it was microwatts per centimeter square.
It was microwatts per centimeter square. Yes, people use different terms. That slide had microwatts per centimeter square. Some people use millijoules or other units of measure, but that particular slide was a 99% dose based on some published studies in microwatts.
Okay, great. Next question from Robert. What happens to viruses that are captured by filters?
So yeah, it's a really good question, and it's a very common question which is asked. So like I said, if you have a fairly decent filter upstream, before your coil system, if it's a MERV 8 or 11, as you saw the air contaminant chart, it's not going to hold the viruses. Even a MERV 11 may not be sufficient for a virus. ASHRAE 241 actually is saying you need 11 or higher, and even a 13 is recommended for that. So the challenge with filters is that if they're not replaced properly, over a period of time, these filters can get clogged, and viruses can release from these filters and get into the airstream. So your filters would be a first line of defense. They're capturing it, but not killing it. So you got to make sure that viruses they may be captured, but they can get released into the airstream. And then UV, of course, comes in and it's actually killing it or inactivating it compared to a filter which is just capturing it.
All right, thanks. Next question we have from Neil. It was suggested to install the lamps parallel to the airstream in ducts. How would you do the service in ducts?
Yeah, I mean, you can, you have to follow what the manufacturer is recommending and what is the lamp configuration which they're recommending in the duct. I showed you a picture of how the lamps are spaced. Some of them could be spaced together. Some manufacturers have a module which you just insert. Some of them, like I said, if you distribute them, you get a better uniformity. So generally from the top or side or from the bottom, you have an access port and you can reach in and mount the lamps. You can have magnetic clips because these ducts are all galvanized steel, so galvanized aluminum. So you can have metallic clips which you can remove and it'll be easy to remove the lamps. But you do need some kind of an access port to reach in and replace your lamps.
Thanks, Ashish. That's what we saw very common during the retrofits that were done during the pandemic, was to add an access door and of course have a switch that would disconnect the power at the same time if that door was opened. Next question from Robert. Is it true that 241 would estimate the ECA for a system that provided log 2 reduction and one with a log 6 reduction as essentially equivalent? That sounds pretty detailed there, Ashish. Is that, I'm going to be able to help with that, or we need to get back with Robert?
I think I'll have to get back to you. From what I think, the efficiency number which is there, the single pass efficiency number translates to an equivalent clean air CFM, but I don't think today the calculator accounts for a higher log reduction. So similar to a MERV, so you get extra points if you have a MERV 11 versus MERV 13. There is some extra points when we have a 90% versus 99%. So 90 to 99, but 6 log reduction anyway, I think it's a really tall order. I think it's a hypothetical question, but I would say that the calculators does account for 90, 99, and maybe 99.9%, but that's the 3 log. But over that, I don't know if the calculator allows for it at this point, but really good question, and I'll have to get back to you on that.
All right, thanks, Ashish. I had a question from Joseph regarding representative in Canada. And Joseph, our international sales manager, Kathy Million, will get back to you on that question. Question, is there any deflector for the UV lights if the UV light shines the filter?
Yeah, so filters, especially synthetic filters, which are made of polyester and synthetic fibers, they are susceptible to UV degradation. So over a period of time, if these filters are replaced, say in 3 months, then it's not so much of a concern. But if these filters typically are replaced after 6 months to 1 year, and they're in direct line of sight of the UV system, can get degraded. Glass fiber filters are actually better in terms of UV degradation. So you need to have some kind of a mesh or some protective layer to protect your filter from it. We do provide a deflector, if you may, which can orient the lamp only in the opposite direction of the filter. But that is only effective for coil disinfection. For airstream disinfection, you want both sides of the lamp to give out the UV energy, so you don't want to block the UV. So yes, you have to have some kind of a deflector or some to protect your filters.
Okay, Scott has a couple of comments. I've seen many UVD, UVR, and stereo systems installed wrong by factories. Material are degrading and units malfunctioning, control wires. And then there was some information from Scott about filters, and then also that the deflectors can reduce the exposure time. I'll address some of the material degradation. Scott, I can let you know that we have recently been working with a number of OEMs and doing degradation testing as they're adding new materials or updating the components that are in their systems. We have the capability in our facility to do degradation testing. We also have a lot of information on material that has been tested, as well as the ASHRAE guidelines do show that too. So it is a focus, we understand that, and I can tell you that the OEMs are taking a close look at that. And reduce, Ashish, I'll let you address this from Scott. He did make the comment that deflectors can reduce the exposure time, as you were talking about that before. So you want to comment on that?
Yeah, so you have to make sure that you have enough irradiance zone for your UV system for airstream disinfection. The exposure time would be reduced if they are beyond, if they are in that irradiance zone. So, but it depends on the size and shape of the reflector, because you also, if it's a metallic reflector, you do get that extra bounce from UV.
All right, thanks. We've had a couple questions on the presentation availability. This is going to be an on-demand video, so as Ashish did, I'm sorry, as Andrew did say early on, that in several days we'll have this available where you can download or we can watch from the website. Can UVC on cooling coils be used to apply towards ASHRAE 241? How would that calculation work?
ASHRAE 241 gives you some credit, and you have to look at your calculator. So if you have other, like I said, you can achieve that overall 241 target by different ways. If we have a filter or if we have some other technology in room, so you're going to get contributions from each. So it all depends on how that system has been designed. So you may get a benefit from what you've installed in the coil as well, but it's going to be way less than a system which is designed for airstream disinfection. So it all depends on what are the other mitigation approaches which you've used for ASHRAE 241. Good question. And I think I have time for one more, Dave, before we end.
Wait, some comments back, deflectors. I think we've covered most everything that's in here. Ashish, if there's any that's left over, I think we're short on time now. We're down to the end. So if there are any presentations or any questions that we didn't answer, we will capture those and get back to you. But I would like to quickly thank all of you again for taking time today to attend. Our next webinar is going to be UVC air purification basics on August 14th. That's less than 2 months away, and I encourage you to sign up. In the meantime, if you need more information, you'd like more information, Ashish, if you can go to the next slide, then here's our team that you can reach out and contact. And this is going to conclude today's webinar. Thanks again for attending.
Thanks for attending, everyone.
Thank you.